Example 2. In a randomized controlled trial in Kenya, insecticide-treated bed nets were tested as a way to reduce malaria. Among 343 infants using bed nets, 15 developed malaria. Among 294 infants not using bed nets, 27 developed malaria. We want to use a 0.01 significance level to test the claim that the incidence of malaria is lower for infants using bed nets. So we're going to test the hypothesis. We're going to construct an appropriate confidence interval based on that hypothesis test, and then talk about what that suggests about the effectiveness of bed nets. This should be bed nets. So the first thing that we want to do is write out our claim. The claim is that the incidence of malaria is lower for infants using bed nets. And in this problem, when we calculate our p-hats, p sub 1 is for infants using bed nets. So if this is reducing the number of incidences of malaria amongst the people who are using bed nets, then we would expect that this P1 for infants using bed nets would be smaller, because when the numerator is smaller, your proportion will be smaller. So the claim is that P1 is less than P2, and that makes the opposite. P1 is greater than or equal to P2. The null is always equals, so P1 equals P2. And the alternative is P1 is less than P2. So that's either your claim or your opposite, whichever one does not have the equal sign. And this one is our claim. The claim is in the alternative hypothesis. Our alpha is 0.01, and we can also look up our critical value. The critical value, because this is a left-tailed test, is going to be negative, and we want to pull up the the normal table in order to find our critical value. So we have a left-tailed test, and our significance level is 0.01, and so we want an area of 0.01 in our left tail. So find the value 0.01 in the table here, and we can see that the closest we have to 0.01 is 0.0099, and so that gives us a critical value of negative 2.3, and from the top 3, so negative 2.33. And then we can go ahead and calculate our test statistic. Before we can calculate that, we need both p-hat1 and p-hat2. P-hat1 is for bed nets. And there were 15 cases of malaria out of 343. That gives us 0.0437. Q-hat then is 1 minus 0.0437. So that gives us 0.9563. Always take p-hat and q-hat out to 4 decimal places. And now we do it for no nets. P2 hat, there were 27 cases of malaria out of 294. So that gives us p-hat sub 2 is equal to 0.0918. And q hat sub 2 is 1 minus 0.0918. That gives us 0.9082. Now we can calculate p bar and q bar. P bar is x sub 1 plus x sub 2 divided by n sub 1 plus n sub 2. That's 15 plus 27 divided by 343 plus 294. Make sure you put parentheses around both the numerator and the denominator with the division symbol in between in your calculators. You should get 0.0659. Q bar is 1 minus that, so 1 minus 0.0659 gives us 0.9341. Now plug all of these into our formula for z. Z is equal to p hat sub 1 minus p hat sub 2, and then minus 0. And this is divided by p bar q bar over n1 plus p bar q bar over n2. In the numerator, we have 0.0437 minus 0.0918 divided by the square root of 0.0659 times 0.9341 divided by 343 plus 0.0659 times 0.0934 divided by 294. So first you need to calculate the numerator, and calculating that difference gives you negative 0.0481. Now hit divided by and then a square root. Make sure you put these both in parentheses, and again, if you have a calculator where you get a square root with a parenthesis, you're going to need to close that off with two parentheses. The first parenthesis will close off this fraction, and the second parenthesis closes off the square root symbol. So once you put this into your calculators, you get negative 2.44 as your test statistic. If you're going to do this in your calculator, then the p-value that you get from your calculator will be 0.0074. We're going to just put our graph right here in the space in the middle that we have. Our critical value is negative 2.33, and our test statistic z is negative 2.44. Because our test statistic is in the tail, we're going to reject our null. Also, since the p-value is less than alpha, that also tells you to reject the null. So if you're going to do the hypothesis test using critical values, then you would create this graph. If you're going to use your calculator and use a p-value, then instead of having the critical value, that's going to be your alpha, which is 0.01, and then instead of z, you're going to write down the p-value. And the p-value is 0.0074. The conclusion remains the same, that we're going to reject the null hypothesis. So going back up to our null hypothesis, because now we need to write out our conclusion statement, we see that the claim is in the alternative hypothesis, and we are rejecting the null. Rejecting the null basically says, quote unquote, that we're accepting the alternative. So that means that there is sufficient evidence to support our claim. So here's our conclusion statement. There is sufficient evidence to support the claim that the incidence of malaria is lower for infants using bed nets. Now we're going to create our confidence interval. This confidence interval, again, is based off of our hypothesis test. Our error formula is z sub alpha over 2 times the square root of p hat sub 1 q hat sub 1 divided by n1 plus p hat sub 2 q hat sub 2 over n2. The critical value that you use here should always be the critical value that you used for your hypothesis test. So that would be 2.33. And this is going to be 0.0437 times 0.9563 divided by 343 plus 0.0918 times 0.9082 divided by 294. When you compute this, you should get 0.0469. So now take the difference that we got from the numerator up above. That difference was negative 0.0481, and we're going to subtract our error, minus 0.0469. This should give you negative 0.095. And then we're also going to add the error, so negative 0.0481 plus 0.0469. This gives us negative 0.0012. And so our confidence interval is negative 0.095 up to negative 0.0012. If you used your calculator to compute your confidence interval, you would get negative 0.095 up to negative 0.0013. So pretty close to what we get when we do hand calculation. And what we can say from this is that 0 is not in our confidence interval, so we can conclude that for sure the two proportions are not equal to each other, and this entire confidence interval is also less than 0, which would make us think that P2 is bigger. That means that there were more incidents of malaria without the use of bed nets. In the next example, in a study of treatment for very painful cluster headaches, 150 patients were treated with oxygen, and 148 other patients were given a placebo consisting of ordinary air. Among the 150 patients in the oxygen treatment group, 116 were free from headaches 15 minutes after treatment. Among the 148 patients given the placebo, 29 were free from headaches 15 minutes after treatment. We want to use the 0.01 significance level to test the claim that the oxygen treatment is effective. So our claim, if we're claiming that the treatment is effective, then that would tell us that P1 should be greater than P2. And the opposite then would be that P1 is less than or equal to P2. The null is always equal, so P1 is equal to P2, and the alternative is greater than. So P1 is greater than P2. The claim is in the alternative this time. We can now find our critical value. So we have a right-tailed test, and our alpha is 0.01. So go to our z-table, our normal table, and we want to find the value 0.01 in our table. The closest value we have to 0.01 is right here, 0.009. That gives us a critical value of 2.3, and then from the top we would get the second decimal place 3. Since this is a right-tailed test, we want the positive value for the critical value, and then we can start calculating everything that we need for our test statistic. So first, people that were treated with oxygen. So that's p hat sub 1, and it's 116 divided by 150. This gives us 0.7733. Q hat sub 1 is 1 minus 0.7733. That gives us 0.2267. And then the placebo, that's p hat 2. That's 29 over 148, and it gives us 0.1959. And then Q hat sub 2 is 1 minus 0.1959, and that gives us 0.8041. Now we can calculate P bar and Q bar. P bar is x sub 1 plus x sub 2 divided by n sub 1 plus n sub 2. Again, don't forget to put your numerator in parentheses and also your denominator in parentheses. This is 116 plus 29 divided by 150 plus 148. And this gives us 0.4866. Q bar is 1 minus 0.4866. And that gives us 0.5134. Now we can plug all of this information into our formula for Z. That's p hat sub 1 minus p hat sub 2 minus 0. Remember, the difference of the proportions is usually 0 in these tests. And then that's divided by the square root of p bar q bar over n1 plus p bar q bar over n2. We have 0.7733 minus 0.1959 divided by the square root of 0.4866 times 0.5134 over 150 plus 0.4866 times 0.5134 over 148. You should write down your numerator. You're going to need that when you go to create your confidence interval. So that's 0.5774. And when you calculate this, you should get 9.97. If you're going to be doing this on your calculator, then you would get a p-value, and the p-value that you would get would be 1.04 e negative 23. So that would be approximately 0. Now we can create our graph. If we're going to do this using critical values, you want to put the critical value on your graph. Our critical value here is 2.33. And then our test statistic is 9.97, and since our test statistic is in the tail, we're going to reject the null. If you're going to use the p-value method because you have a graphing calculator and you want to use your graphing calculator to do these calculations, then instead of your critical value, you're going to have alpha, which is 0.01. And here, instead of z, you're going to have your p-value, which is 0. Again, the p-value is less than alpha, so that would tell us to reject our null hypothesis. Now we need to write out our conclusion. So go back up to the null hypothesis. We are rejecting the null, which basically says that we're accepting our alternative, and so that tells us that we do have sufficient evidence to support our claim. So our conclusion is that there is sufficient evidence to support the claim that the oxygen treatment is effective. Now we want to create a confidence interval based off of this hypothesis test. The error equation for this is z sub alpha over 2 times the square root of p hat sub 1 q hat sub 1 over n1 plus p hat sub 2 q hat sub 2 over n2. And we always use whatever critical value we used in the test for this. So that's going to be 2.33 times the square root of 0.7733 times 0.2267 over 150 plus 0.1959 times 0.8041 divided by 148. So the error that you get here is 0.1101. Now we subtract that from the difference of the numerator in our calculation up above. That difference was 0.5774 minus our error of 0.1101. This gives us 0.4673. And then 0.5774 plus our error, 0.1101. This gives us 0.6875. If you used your calculator in order to compute this, then you would get the confidence interval 0.46745, 0.68732. So because 0 is not in this confidence interval and the entire confidence interval is greater than 0, we can conclude from that that the proportion of incidence of having malaria when you use a bed net is greater than when you do not use a bed net. So that is it for testing the claim about two proportions. Let me know if you have any questions, and I hope you're having a wonderful day.